Okay. All right, so like I mentioned, we are going to start chapter 6 today. Okay, we get started with chapter 6. Chapter 6 is a very interesting, very new topic about inductance and capacitance. Okay, so far, the circuit elements that we discussed so far are voltage source, okay, and a current source. Okay, we discussed the idea of a current source. Okay, and a dependent voltage source, dependent current source, and of course a resistance. These are all the circuit elements, maybe battery, which is the voltage source again. So the idea is we looked at a few circuit elements, but these are just a handful of them. There's more um, different varieties of circuit elements, inductance and capacitance. Okay, so we are going to look at what an inductance is, what a capacitance is, how they behave, and what is the relationship between the voltage and current between them. Okay, this is more or less the idea that you will understand for just about any circuit element that you encounter. If you go on to triple E or CPE majors, computer engineering or electrical electronic engineering majors, okay, you'll see more circuit elements like MOSFETs, BJTs, bipolar junction transistors, okay, different kinds of transistors, inductor, diodes, okay, so on and so forth. Even when you talk about these devices, you'll try to understand the relationship between the voltage and the current, okay, relationship between each of these devices, the relationship between current and voltage in each of these devices. So if you want to gain a very good understanding of a device, of the terminal behavior of a device, okay, how it behaves with respect to its terminals, then you try to see what is the current that's flowing in this element in response to the voltage that we apply across it. Okay, so that's the idea that gives us intuition about the terminal behavior of any circuit component element. Okay, even so, we'll do the exact same thing for inductors and capacitances as well. By the way, the symbol for inductance is a um, winding, a wire that is wound around itself. Okay, the inductance for capacitance, the symbol for capacitance is that guy. Okay, the notation, the alphabet that represents inductance is capital L. Okay, L represents capacitance, and C represents capacitance. L represents inductance. L represents inductance. C represents capacitance. Okay, fundamentally, at the core, the operation of capacitance comes from the fact that charges are separated. Okay, there's no current actually flowing through the capacitance. Okay, in between two parallel plates is an insulator. Okay, that guy is an insulator. Okay, when you have charges, positive and negative charges, separated by some insulator, that's the construction of a capacitance. Okay, simply separation of charges. Inductance, on the other hand, is the magnetic artifact of an electric current I flowing through a winding. Okay, so it's a magnetic artifact of electric field that is flowing through a winding. Okay, so that's the idea of inductance. And then there's the idea of capacitance. Okay, capacitance and inductance. So fundamentally, these are two new circuit components that we are going to discuss. Okay, this is a wire, a winding, okay, coiled wire. So earlier we defined voltage to be an artifact of separation of charge. Remember when we talked about charge, okay, separation of charge and flow of charge. Okay, two things can happen with charge. Charges can be separated. Okay, that leads to voltage, right? Voltage is separation, an artifact of separation of charges. Current is an artifact of flow of charges, the rate of flow of charge. That's what we define to be current. Okay, so capacitance manifests that idea. Capacitance, okay, when you store charges in a capacitance, okay, when you separate charges in a capacitance, this is called a parallel plate capacitance. Okay, that's the idea of a capacitance, right? It's an artifact. It's causes separation of charges through an insulator, causes a capacitance, and then the flow of current. Okay, the movement of charge that's used to define the current. That's also used to define the idea of inductance. Okay, so separation of charge leads to voltage. Okay, so voltage is set up across a capacitance and current through the inductance. These are the um, independent parameters. Okay, that's the input to the capacitance. We apply varying voltage. The input to the inductance is current. Okay, so I mentioned I versus V is a relationship that we have to thoroughly understand to understand the behavior of any circuit component. So here is the relationship between the current in a capacitance. Okay, the current in a capacitance is proportional to the rate of change of voltage. Okay, if the rate of change of voltage is constant, or if the voltage is constant, that implies the rate of change of voltage is zero, right? If the voltage is constant, it's a change. The rate of change of voltage is zero. That means the current in a capacitance, the current displacement current in a capacitance, and it's a little different. I'll talk about that in a second. But the current, the capacitance current will be zero if there is constant voltage across that. If there is no voltage changing across the plates of the capacitance, then the current is zero. Okay, so the idea is I is CV by C dV by dt. Okay, where C is the capacitance of the capacitor, V is the voltage, the derivative of voltage with respect to time. Okay, that's the slope of voltage versus time. Okay, so the idea of IV characteristics. Okay, the current in a capacitance, the current across a capacitance. Okay, or the displacement current, to be accurate, changes in response, that is the derivative of the voltage applied across it. Okay. For the inductor, on the other hand, the IV relationship appears like this. V is L di by dt. Okay. The rate of change of current, that is proportional to the voltage across an inductor. Okay. So what you want to understand is, in the capacitance, this guy is the independent input and the current is the dependent output. So this guy is the input, this guy is the output. Okay. Similarly, in an inductance, the voltage that is set up across the um, terminals of an inductor depends on the current. Okay. So here is the independent input, this guy is the output. Okay. So that's the output of the uh, inductance. Okay. That's the output voltage of an inductor. The voltage across an inductor VL is proportional to the rate of change of current, where L is the proportionality. Okay. Similarly, for a capacitance, the current is proportional to the voltage applied across the capacitance. Okay. So what I want to mention, maybe I'll mention that in the next slide, is that there is no capacitance, there's no current flowing through the capacitance. It's only displacement current around the terminals. I'll talk about that. Okay, let's talk about inductor. Let's take a closer look at the inductor. Okay, the inductance, the symbol of inductance is shown here. Okay, that represents a winding. The alphabet used to represent inductance is L. It's a consequence of a conductor carrying a current, and it's an artifact of the magnetic field of the current. Okay, the voltage across an inductor is written in accordance with the passive sign convention. The voltage, okay, if there is a plus sign that you choose over there and a negative sign that you choose over here, okay, the voltage and the passive sign convention dictates that the current flows from higher potential to lower potential. Okay, so here is the expression for L di by dt. Once you remember this, if you wanted to get an expression for the current in an inductance, the current in an inductance is 1 over L integral T naught to T0 VL dt plus initial condition. Okay, that represents the initial condition. Okay, so here is the expression for voltage versus current relationship in an inductance. Okay, the units of inductance is Henry, shown using H. Okay, so compare this idea. V is L di by dt with the idea of V is I times R. Okay, there is still some similarities that we can see in the resistance. Okay, the voltage is proportional to the current. The voltage that is set up across the terminals of a resistance is proportional to the current that's flowing through it. Okay, so the constant of proportionality here is R. Okay, then V is IR. Okay, that's the idea of a resistance. But in inductance, the voltage is proportional not to I, but to the slope of I. Okay, that's all there is to an inductance. The rate of change of the current that determines the voltage across this. And now L is simply a constant of proportionality. Okay, V is L di by dt for an inductance. Okay, so let's see the behavior of inductance voltage current relationship is derived from the resistance. It is very similar to the resistance. As you can see, voltage here is proportional to current, voltage here is proportional to the slope of current. That's all there is to the resistance. It's the slope of change in current that creates a change in voltage across the inductor. Okay, if here is the idea. Let's say I'm plotting current versus time through an inductance. Okay, according to this relationship here, according to the L di by dt relationship, where do you expect, what do you expect the voltage to be? You guys?
Should it be constant
Should be
there?
constant, somewhere around here. And this constant, this value, represents the slope of this guy. Okay, the slope of this guy, if it comes out to be, I don't know, L1, that value sets the voltage across. So this is the voltage across the inductance. Okay, so what do you think happens if if the current is not increasing across an inductance? So this is the current across an inductance, right? So what do you think happens if the current flowing through an inductance is constant? If that's the current, what do you think happens to the value of the voltage across the inductance? It will be the slope of this guy, which is zero, right? So the voltage across an inductance is zero because the slope of the current is zero. It's horizontal line. So in other words, if a constant current is flowing through an inductance, okay, then the voltage dropped across the inductance, the voltage across the terminals is zero, okay, because the voltage is proportional to the change in current. If a current is constant, the change in current or its derivative is zero, meaning the voltage across the terminals of an inductance is zero. Okay, so that's the idea. If the current through an inductor is constant, then the voltage across the inductance is zero. Okay, so that's the idea of um, voltage across an inductance. All right. Okay, now we can do the power. Power is V times I, right? Now the voltage across an inductance is L di by dt. So the power stored in an inductor's magnetic field, and by the way, both cap and inductor can store energy. It can be used to store energy in different forms. Okay, in inductor, it's stored in terms of magnetic field. Okay, power stored in an inductor is L times I times So I times V, V is L di by dt. Okay, so that's the idea of the product of voltage and current across that pipe. The energy that an inductor can deliver to the load is given by this formula, 1/2 Li squared. Okay, this is a familiar form for energy that we know. 1/2 mv squared, the energy, kinetic energy of a body of mass m moving with a velocity v. That's the kinetic energy of a moving body, right? 1/2 kx squared. That's the energy stored in a spring. K is the spring constant, x is the compression. Okay, so energy stored in a spring. So this form of 1/2 some term times a squared term. Okay, that's a very familiar form for energy. The energy stored in an inductor, the energy that the inductor can deliver to the load is 1/2 Li squared. Okay, it's simply the rate of power delivered. Okay, so that's the idea of an inductance. Inductance is simply a winding, a wire, a coil. Okay, a coil, a changing current in an inductance sets up a voltage across it. Okay, the rate of change of this current determines the voltage across the inductance. That's the idea. Let's look at the other circuit component, which is the capacitance. Okay, that's the cap. Okay, the capacitance is the consequence of charge separated by a dielectric or an insulator. So all it is simply two parallel plates separated by an insulator. Okay, that's all there is to it. This guy is insulator. Okay, so what happens is if I apply some positive voltage on one side and negative voltage on the other side, okay, there is electric field. There's no current here. The current flowing through a capacitance is zero, but there is current around the capacitance. Okay, that's a slight difference that we'll discuss later. Okay, but the idea is in between, through the insulator, inside a capacitance, there is no current. There's no current through a capacitance. But in response to the changing voltage across the terminals, the displacement current around the capacitance changes. Okay, we'll talk about that in a second. Okay, but here is the construction of a capacitance. Capacitor. Okay, so a capacitor, the symbol for that is C. It's a consequence of charge separated by an insulator. Okay, you'll see this coming into play over and over and over again in a bunch of different places that you don't expect. But then whenever you see charges separated by an insulator, that leads to some kind of capacitance. So if you have an electric wire going, carrying current in the north, and right below it is another charge carrying conductor, and there is some air in between them, some dielectric, some insulator between them. Inadvertently, even without you making an effort to create a capacitance, that automatically leads to some kind of capacitance. Okay, so you'll see this come up in places that you least expect. Okay, so the idea is when charges are separated by an insulator, that leads to a capacitance. Okay, so the current in a capacitance is proportional to the changing potential. Okay, the voltage across the capacitance in response to the slope of that. Okay, the current across the capacitance changes. So C is the constant of proportionality. C, I is C dV by dt. Earlier in an inductance, L di by dt, the voltage across an inductance was L di by dt. The voltage set up across the terminals of an inductance that was proportional to the current that you apply, the rate of change of current that you apply. Here, the other way around, the current, displacement current around a capacitance is proportional to the potential, the rate of change of voltage across its terminals. Okay, and we can express the VC, the voltage across a capacitance, in terms of the current across its terminals. Okay, so it's a displacement current due to a time varying electric field. The current, the charge separation is due to displacement current around the capacitance. There's no current flowing through the capacitance, but because of the voltage drop across the terminals of the capacitance, it changes the amount of current in the circuit around its terminals. Okay, so here is the voltage sign and the direction for the current in accordance with the passive sign convention. Okay, the unit of capacitance is farad, F. Okay, so we looked at inductance in which the voltage is proportional to the slope of the current. Similarly, the current in a capacitance is proportional to the rate of change of voltage or the slope of voltage. Okay, the capacitor acts as a twin of an inductor. The capacitance acts as a twin of an inductor. It's the slope of change in voltage, okay, that creates a constant displacement. Again, V was proportional to I in a resistance. Okay, in a capacitance, the current around the terminals of a capacitance is proportional to the change of voltage, the rate of change of voltage. Okay, if the voltage across a capacitance is constant, then the current, um, around the capacitance is zero. Okay, so this is something you want to remember. Capacitance. Okay, let me mention this. Let's see. I'm going to do this and give you a piece of information that you want to remember for the rest of your career as engineers. Okay, let's say I'm plotting voltage on the x-axis and current and time on the y-axis, and the other way around. The time on the x-axis, voltage on the y-axis. Okay, if this is the voltage for a around a capacitance, okay, the voltage across the terminals of a capacitance is constant, then the current is really zero. Okay, because the current is proportional to the slope, right? So the principle, the current in a capacitance is zero if the slope of the voltage is zero, or if a constant voltage is applied. So the idea that you want to remember is capacitance acts as open circuit to DC. Okay, DC is simply a non-time varying constant voltage to DC voltage. When you see a DC voltage of 5 volts, 10 volts, 100 volts, doesn't matter. As long as its value is constant, as long as the voltage is constant, and it's not time varying, then it's a DC, constant DC. The magnitude doesn't matter. Okay, and when the voltage across the capacitance is constant, then the capacitance acts as an open circuit. Okay, meaning that there's no current flowing through it. What is the idea of open circuit? The idea of open circuit is that the current flowing through the terminals, or the current displacement current, because of the capacitance, is zero. Okay, the current around the capacitance is zero if the voltage across it is constant. Okay, so let me be the first person to tell you that the voltage being constant around the terminals of a capacitance, its current is zero. Okay, similarly, I'll give you another example. Let's say I'm trying to plot the voltage as a function of time. Okay, this guy is the voltage. Okay, if the voltage is a sinusoid, okay, then the current in response to this voltage, if this is a sine, the derivative of sine is cosine, right? The derivative of sine is cosine, which is going to appear, which is going to appear like that. Okay, so style that to be this guy. Okay, maybe this guy. Okay, so let's see if the input voltage is this guy, then the resulting current is the derivative of a sine wave. That's the current across a capacitance, okay, which is really a cosine wave, cos wave. Okay, so similarly, if the voltage is constant, then the current is zero. Okay, really the current is the derivative of the voltage. Okay, now we can define the power. Okay, the power stored in capacitance electric field is C, dV by dt is I, so I times V. The very familiar definition of power is VI. Okay, in place of V, I leave it as V. In place of I replace it with C dV by dt. Okay, here again is our familiar half kx squared formula. 1/2 Li squared was the energy stored in an inductor. 1/2 CV squared is the energy stored in a capacitance, energy that a capacitance can deliver, where C is the capacitance value, and V is the voltage applied across the capacitance. Okay, so the idea is that the energy stored in a capacitance, or the energy that it can deliver to the load, is 1/2 C V squared. Okay, a resistor, okay, a resistor had a resistance R. Okay, V, the voltage across the resistance is proportional to the current, and the constant of proportionality is resistance. Similarly, the current, the displacement current around the terminals of a capacitance is proportional to the rate of change of voltage, and the constant of proportionality is capacitance for a capacitor. Just like resistance characterizes the resistor, capacitance is the value that characterizes the capacitor. Okay? Questions, please. Questions so far. Okay. Now, very interesting, very simple concept here. What happens when you put capacitors in parallel or inductors in parallel or series? Okay. Earlier, we investigated the idea of having a bunch of resistors in series. Okay. Now we want to understand what happens if I put inductors in series and capacitors in series. What happens when you put inductors in parallel and capacitors in parallel? Okay, so spoiler alert here, resistance or the inductors in series behave like resistors in series. Okay, meaning that if there are three different inductors, L1, L2, and L3 in series, the equivalent inductance is simply the sum of inductances. Just as in resistance, the equivalent resistance in series is the sum of individual resistances. Inductors in series behave like resistances in series. On the other hand, capacitances in series behave like resistors in parallel. Okay, we'll look at that. This is simply something for you to bear in mind, just so it's easy to look at what's going on. Okay, a series combination has the same current. Okay, when you have a bunch of different inductors connected in series, the current flowing through them is the same. So what you can do is you can look at the individual voltages across these terminals and then add them up. The overall voltage that is applied from here to here, that's V, that voltage is the sum of individual voltages, and you can derive the expression that what matters is that the equivalent resistance of a series resistances is simply the sum. Okay, just like in resistors, the same applies in inductors as well. Okay, this is inductances in parallel behave similar to resistances in parallel. Okay, remember, if you remember the fact, when you have a bunch of circuit elements connected in parallel, the voltage across each of those elements remains the same, remains a constant. So using that principle, you can find out that when inductances are connected in parallel, the 1 over equivalent resistance is the sum of 1 over individual inductances. Exactly same for parallel resistances. Equivalent resistance, the reciprocal of that is equals to the sum of reciprocals of individual resistances. Okay, that's the exact same behavior for inductors. Okay, so we'll come back to solving this problem. Let's see if we can do the exact same analysis for capacitors. Okay, let's start with capacitances in parallel. If I have three capacitances in parallel, the equivalent capacitance is simply the sum of individual capacitances, owing to the fact that the same voltage is applied across all the three capacitances because they're in parallel. Okay, you can do the simple analysis. You can sum the currents through all of these capacitances and find that the equivalent capacitance is the sum of individual capacitances when connected in parallel. Okay, that's the exact similar behavior. So caps in parallel behave similar to resistances in series. Resistances in series add to give an equivalent resistance, while capacitances in parallel add. Okay, and by the same analogy, when you connect capacitances in series like so, okay, the equivalent capacitance, the reciprocal of that is going to be the sum of reciprocals of the individual capacitors. So series capacitors behave like parallel resistances. Okay, that's all there is to it, and the um, rest is all simple mathematics. Okay, so resistances, capacitances, inductances in parallel. Now let's do a problem. The problem is um, there are two inductances here connected in parallel. So what we want to do is the the current for one inductance is given. So you know the current flowing through this inductance. You know the current flowing through the other inductance as well. And you're asked to find out. Let's see, you're asked to find out um, the initial current, okay, in the reference direction. What is the initial current and its reference direction in the equivalent inductor? Okay, so there are two questions. What is the equivalent inductance of two parallel inductances? Okay, when inductances are in parallel, that's the equation similar to that of parallel resistances. Okay, L1, L2 by L1 plus L2. So you get the parallel equivalent of two inductances, 60 ohms and 240 ohms, is less. So the L equivalent is less than L1. L equivalent is less than L2 as well. So the equivalent inductance of L1 and L2 in parallel, okay, the overall equivalent inductance is less than the smallest inductance, smallest of L1 and L2. Okay, so similarly, if you have 10 ohms and another 10 ohms connected over here, the equivalent of these parallel combination, you know for a fact, is less than either of those. Similarly, if you have 5 ohms and 1 ohm connected here in parallel, the equivalent of two parallel resistances is less than the lowest of the resistances. So the equivalent resistance is less than either of those. Similarly, a quick sanity check when you do your problems is that the equivalent resistance is less than either of those values. It's less than 60, it's less than 240, it's less than the least value of the inductance in parallel. That's a sanity check. Okay, so what is the initial current? So that's first problem. What is the initial current and its reference direction in the equivalent inductance? Okay, so here is the equivalent inductance, which is given to be 48 millihenry. Millihenry. Okay, so the equivalent current is that I2 is negative 5 amperes. Okay, if you think about it, I2 is given to be negative 5 amperes. I1 is given to be 3 amperes. I1 is given to be 3. I2 is given to be negative 5 amperes. So okay, the current flowing initially, the current flowing through these inductances should be 3 amperes minus 5 amperes, which is a negative 2 amps. Okay, that's negative 2 amps. So that's therefore that's the initial current I of T naught is 2 amperes flowing upwards. Okay, to represent this negative sign here, there's an inversion of the direction over there. Okay, the inductance, equivalent inductance is 48 millihenry, and the current is 2 amperes going upwards. Okay, going upwards because the voltage drop is set up in this direction. Negative 2 amperes is opposite to the passive sign, is opposite to the polarity of the voltage, positive to negative. Okay, the next question is find the expression for I as a function of t. Remember, this is I at time t0. Okay, initial value for the current. Now, if the voltage across an inductance is given to be this guy, okay, we know for a fact the voltage across an inductance is L di by dt. Okay, so if you wanted to find I, you'd have to do the integral of the voltage. Okay, so this is the voltage. That's the voltage. So I is integral. So you bring this volt inductance to the other side. So that is 1 over L equivalent 0 to t v of t dt. Okay, so that is what you would need to do to get the expression for current. Okay, this is coming from the fact that V is L di by dt, and in order to get an expression for I, you'd have to integrate the voltage. Okay, once you do the integration, once you do the calculate the integral, you're going to be left with, so this is the initial condition, the negative 2 amperes that we found out earlier. Okay, that's the initial condition all along. Okay, and this guy is calculated from the integral. Okay, once we calculate the value, this is going to be the expression for current. This is going to be the expression for current here. Okay, so for this voltage, for the voltage that is negative 30 e to the negative 5t millivolts, the current, the equivalent current setup is that guy. Okay. In order to verify this, so my contention is that this is the current as a function of time. Let me see what happens at time t equals to 0. What is the value of current? All you'd have to do is to plug in a value of 0 here. Okay? Excuse me. Sorry about that. So all of this goes to the power goes to 0. E to the 0 is 1. So what you have is negative 2.125 plus 0.125. So that's a value of negative 2 amperes. Remember, that was supposed to be the initial current that we found. Okay, at t equals to 0, I at t equals to 0 was to was calculated to be 2 amperes. Okay, 2 amperes of current as the initial condition at time t equals to 0. So when you plug t equals to 0 in this equation that you got for, in the expression that you got for the current, it's going to lead you back to the negative 2 that you assumed was going initially. Okay, so all you had to do was to apply, just like the question is similar to V is Ohm's law. Okay, so if V is given and you are expected to find I in an inductance, what would you do? You would simply divide the voltage over the resistance. Application of Ohm's law to get the current. Similarly, in this problem, um, V is L di by dt. Okay, in this case, V is given. You calculated the equivalent L. You are asked to find I. So you rearrange this equation. I is 1 over L integral 0 to t V of t dt. Just like you rearranged V equals to IR formula, it's just a matter of rearranging and calculating the integral. Okay, that's all there is to it. Okay, let's look at another similar problem. Similar problem for capacitances in parallel. Okay, the voltage is given. Initial voltage at T0 in one capacitance is given. The initial voltage for another capacitance is given to be negative 5 volts. So this is negative 10 volts across this capacitance, and across the other capacitance is negative 5 volts. Okay, the current, these are connected in series, so the current flowing through this guy as a function of time is given. Okay, you're given an expression for the current as a function of time. So you're asked to find out a couple of things. What is the equivalent capacitance? That's the first thing you're asked to find. Well, in order to find the equivalent capacitances in series, all you have to do is 1 over C1 plus 1 over C2 will give you 1 over C equivalent. Okay? So if you wanted to calculate just the C equivalent, you do this guy. Okay? And as you can clearly see, two resistances, two inductance, two capacitances, when they're connected in parallel, in series, 2 microfarads and 8 microfarads. Okay, the equivalent capacitance is less than the lowest. Okay, the equivalent capacitance is lower than the lowest. Okay, from this we can find out the equivalent capacitance, C1 C2 by C1 plus C2. That's A, done. Okay, B is what is the initial voltage across the equivalent capacitance. So there's a negative 10 volts across here. There's a negative 5 volts across here. Okay, so the equivalent is going to be simply the sum of these two. Okay, the equivalent capacitance is going to see a voltage of negative 15 volts, okay? Because you can write the KVL equation and find out that the voltage across this capacitance is simply negative 15 volts, the equivalent capacitance. All right, so now the third problem is I is given. Okay, you know I in a capacitance is C times dV over dt. Okay, so I is given, you're expected to find V. That's part C that you're going to see. So in order to do that, all you have to do is V is 1 over C integral 0 to T I of t dt plus I at t0, okay, plus any initial condition plus I at t0, okay. That will be the effort for you to do. It's simply rearranging of this characteristic equation of a capacitor. I in a capacitance is C dV by dt. So if you wanted to find V, you'd have to rearrange. That's all there is to it. Okay. So in order to find V, you rearrange in terms of 1 over C, I of t dt plus the initial condition. The rest is just application of the integral. Okay. Or the application of the integral, and then you'll find um, an expression for let's see, where did that expression go? Okay, e to the 150 over this guy. Okay, okay. So the question really is, what is the value of voltage across C equivalent as t tends to infinity? Okay, so the first thing we do is to apply 1 over C equivalent integral I of t dt. So all of this is I of t, including this guy, dt. You do the derivative of it, okay? And you plug in t is infinity. When you plug in t is infinity, you get a value of 0. Okay, so simply the application of just like V is IR, you're given one term and asked to find out the other. Similarly, I is C dV by dt. Okay, you're given an expression for I, you're asked to find out V. Okay, so you simply rearrange dV over dt is 1 over C times I, and V would be integral I of t dt from 0 to t. Okay, so plus any initial condition that you may have. Initial voltage that is already in the capacitance. Okay, so that's all there is to the idea of capacitance. Okay, time varying quantities, that you simply have to integrate. Questions, please. Questions so far? Okay. So I want to stop here. We'll come back on Monday, look at a couple of problems, and also do some review before the midterm. Before the midterm on when's the midterm again? Let's see. There is an exam on Tuesday, right? 6:23. Okay. So in the meantime, look at some example problems in chapter 6. Work on that over the weekend. So I wanted to talk about this. So as you know, We have been ahead of schedule and we are ahead of schedule. We were not scheduled to handle this chapter 6 until Monday. But owing to the fact that you guys are extremely sharp, you're fast, and you're accommodative of the advanced pace here, we are able to get done with chapter 6. So you can look at it over the weekend. Okay. Friday through Monday, you have some time to look at that. We'll come back and review chapters 4, 5, and 6 for the exam. Okay.
Professor, one question for Monday. If we have questions, can we bring you questions? You could do them during class.
Yes, we can try that.
Also, at what time will you post the video, or does it post automatically on YouTube?
I usually post them within 1 or 2 hours of.
Okay, perfect. Thank you, Professor.
Yes, of course. So sometimes what happens is I definitely post the video within 1 or 2 hours. I may just forget to add it to the playlist. So what you can do is you can go into my channel, look at the videos uploaded, and then if you don't find it on the playlist, it's you may want to look at my uploaded videos as well.
Got it. Thank you so much.
While you're there, just a shameless plug, like, comment, and subscribe. Like, comment,
Thank
and
you.
subscribe to my YouTube channel. All right. So we'll stop there. We'll come back on Monday and we'll look at
Thank you,
some
Professor. Have a
topics.
great day.
Take care.